Welcome, this is Mrs. Nearing, and in this video we're going to go through some more sample calculations on how you can use ice charts. And remember, when you're using ice charts for equilibrium problems, there's two general types of problems you might see. One is where you're using concentration or pressure information to find the value of K, and then the second scenario is if you are given the value of K and you are trying to find concentration or pressure. So this video goes over problem type number 1. If we're given some information about concentration and we're trying to solve for the value of K. And we're going to look at applying this in two different scenarios if you're dealing with acids and when you're looking at the solubility of an ionic compound. Okay, so we've got this example number 1 with an acid. We're looking at nitrous acid, which is different from nitric acid. It has HNO2 rather than HNO3. And it dissociates in water according to the chemical equation shown below. So acids, when they dissolve in water, they will break apart into ions, kind of like ionic compounds do. Strong acids will do this completely, and we think of it as almost being like a one-way arrow. But other acids that are not qualified as strong, we call them weak acids, and they will just kind of do this partially. So they're going to make some products, but they're still going to have some reactants, and they're going to have actually mainly reactants left over. We don't make a whole lot of products. So this is an equilibrium system, and we can solve to find the equilibrium constant for this reaction. All right. So we've got some information. We've got an initial concentration of your acid, and then we are given the pH. And so if you look on your equation sheet, there's a formula, I should say, that says this right here. pH is the negative log of the H plus concentration. So if we know the pH, then we can determine the H plus concentration in your solution. And that is going to be the H plus concentration at equilibrium. So basically, if you're being given a pH, you're being told what the H plus concentration is at equilibrium, and then we can use that to calculate the KEQ for this reaction. So I'm going to go to the next page, give myself some more room to work. So here's our scenario. First, I'm going to write a K expression for this reaction. So it's going to be products over reactants. So my products are these two ions. The reactant is HNO2. They're all aqueous. They all get included. This is otherwise known as a Ka expression because HNO2 is an acid. So we call the K expression for an acid a Ka. But notice it's the exact same thing as a Kc expression. So really nothing new here. All right. We are given the pH, and we need to calculate the H plus expression. Excuse me. So pH is the negative log of the H plus concentration. So the inverse of log is doing 10 to the. So let's kind of rearrange this real quick. So we can multiply both sides by -1, just to simplify that here. I'm just justifying my algebra here. So negative pH equals the log of the H plus, and then we would raise both sides by 10 to the. So you end up with like 10 to the negative pH is equal to the H plus concentration. Hopefully you could follow my algebra to see where I got there. So the H plus concentration is 10 to the minus pH. So in this problem, 10 to the minus 2.02, stop and plug that into your calculator. You can use the little, like caret symbol there. You end up getting 0.0095. Turns out this number will only have 2 sig figs in it. We'll talk more about sig fig rules later. So, okay. Now we're going to go over here and we're going to set up an ice chart. So I'm going to go I, C, E. I'm going to look at the problem and say, what do I know? Well, we make a solution that is 0.2 molar HCN. So that sounds like an initial concentration of my HNO2. So initially we just dissolve some HNO2 in water, enough to make it 0.2 molar. So initially we haven't added any of these ions. These ions are going to get produced from my reactant dissociating. So then once we dissolve the HNO2 in water, it's going to dissociate, it's going to make some ions. We measure the pH, and the pH tells us the concentration of the hydrogen ions that are made. So that's your equilibrium concentration of hydrogen. So notice how we've got some initial values. We have at least one equilibrium value. So we're going to be able to figure out the value of change. So it looks like my hydrogen concentration went up by 0.0095. And then once I know one of the change values, I can fill in all of the change values. They're going to match your stoichiometric coefficients. And in this reaction, notice how it's a 1-to-1-to-1 ratio, so that makes it easy. So if we made that many hydrogens, we also make this many nitrite ions because they're in a 1-to-1 ratio. So the concentration of nitrite is going to be the same. And then you are going to use up that much of your reactant. So remember, the sign on the right is going to be opposite the sign on the left. So if you're making product, you're using up reactant. So if I take 2 and negative 0.0095, I get 0.191 if I round it to the right number of sig figs. Then I'm going to go over and plug that into my K expression. So notice K is 0.0095 times 0.0095. You could write that as 0.0095 squared if you would like, divided by 0.191, and you end up with 4.7 times 10 to the negative fourth. You can't really see the 4 there. Okay, so that's one example with an acid. So the key thing to keep in mind is that the pH is going to tell you the hydrogen ion concentration at equilibrium. That's like something to keep in mind when you're looking at this type of problem. Okay, so let's look at another example. And in this example, they give me something about percent ionization. So this is the information presented in a little bit of a different way. Instead of saying, here's how many ions you have at equilibrium, this value is telling me how much reacts. So this value is basically telling me some information about the change rho. So we're starting with a certain amount of acid, and then 1.3% of that is going to get used up. So I'm going to be able to fill in a value in my change rho, and then I'll be able to use that to fill out the rest of my chart. So let's go to this next page and see what I'm talking about here. All right. So I'm going to start up by writing my Kc expression. And again, it's my products over my reactants. I'm using brackets because it is a Kc. It's going to look like this. So coefficients become exponents, but all the coefficients are 1. And we call this a Ka because this substance is an acid. And I can tell it's an acid because it is making H+ ions. That's one of the ways you can spot it's an acid. All right, now I'm going to set up an ice chart and look at the problem and see what the problem tells me. So I'm starting with 0.1 molar acetic acid. So basically think of it, you dissolve some acetic acid in water and you made it so that the concentration is 0.1 molar. So initially you don't have any of these ions. And then a reaction occurs, and in this reaction, somehow, we know that 1.3% of my acetic acid is going to ionize. So what that means is 1.3% of it reacts. So I want to know what is 1.3% of 0.1 molar. So I'm going to take 0.013 times 0.1 molar, and that is 0.0013 molar. So that is how much of my reactant gets used up. Remember, once you know one of the change values, you know all of the change values because they react in a stoichiometric ratio. And this problem is a 1-to-1-to-1 problem. So if this decreases by 0.0013, this is going to increase by 0.0013. And then same over here. So that's why they call it the percent ionization. We're saying what percentage of your original acid turns into ions. So 1.3% of these 0.1 moles is being turned into ions over here. Then I'm going to figure out my equilibrium value by adding these up. So I end up getting 0.099, 0.0013, and 0.0013. Then I'm going to go and plug these into my K expression, which I wrote. So it's 0.0013 times 0.0013, so I'm just going to write squared, and 0.099, and you end up getting about 1.7 times 10 to the negative fifth. We've got 2 sig figs here. All right. So those are two acid examples. And now let's look at an example of solubility. This is another equilibrium application you might see. Silver sulfate is something that, according to our solubility rules, we would say that silver sulfate is insoluble. So it is not very soluble in water. However, even those things that are insoluble, when you dump them in water, actually a tiny bit of them do dissolve. And so when you add enough silver sulfate to water to make what we call a saturated solution, what it means when you're saturated is that you are at equilibrium. Whoops, excuse me. So whenever you see the word saturated, read that to mean equilibrium, which means that this reaction is proceeding both directions at an equal rate. So some of your silver sulfate is dissolving to form ions. At the same rate, these ions are coming back together and reprecipitating back out to form the solid. So saturated solutions exist in these equilibrium systems, and since it's an equilibrium system, I can write a K expression, I can use an ice chart to solve for a variety of things, so let's give it a try. So first we're going to write a K expression. So it's going to be products over reactants. So silver is a product. And then sulfate is a product. And then I have a reactant, but notice that the reactant is a solid. And we don't include solids in our K expression. So we're just going to divide by 1. So this is it. This is my K expression. There's no denominator. So solids and liquids get left out of K expressions. So now I'm going to set up my ice chart. And since solids get left out of my K expressions, I can just kind of ignore them when I'm setting up my ice chart. We're not going to have any information about molarity, and it doesn't go in our K expression, so we just ignore that, scratch it out. And if you think about what's happening here in this system, let me go back to this previous page. This reaction is describing solid silver sulfate dissolving in pure water. So we imagine that the initial concentration of ions is 0, because we're talking about what happens when it dissolves in pure water. So initially, these concentrations are 0. Then you dump the silver sulfate in, it reaches equilibrium, and when it reaches equilibrium, so notice here at equilibrium, we observe that the silver ion concentration is this. And how do we observe that? Maybe we precipitate it out and do some gravimetric analysis. We do a variety of different things there. So this is our concentration of silver ions. So I've got an initial, I've got equilibrium, so I can work my way backwards and figure out what the change was. And then I can use my mole ratios to figure out what the other change is. So this is a 2-to-1 mole ratio. So my change in silver is going to be double whatever my change in sulfate is. So in order to find the change in sulfate, I'm going to take 1/2 of 1.2 times 10 to the negative fifth. And I'm adding it, because they're on the same side of the arrow, so they're both increasing in concentration. And 1/2 of 1.2 times 10 to the negative fifth is 6.0 times 10 to the negative sixth. And now I have equilibrium values for both of my products. I don't have anything for my reactant, but that doesn't matter because it's not part of my K expression. So I'm going to go over here and I'm going to plug these into my K expression. This is 1.2 times 10 to the negative fifth. This is going to be squared. And then this is 6.0 times 10 to the negative sixth. All right, so my answer is going to be 8.6 times 10 to the negative 16th. And remember, our K values are unitless, even though this seems like it should have a unit. By definition, it does not have a unit. All right,